Hey everybody, in this video we're going to be talking about linear transformations. Okay, so let's define what that means. A transformation, you can just really think of it like a function, or another way we talk about this is called a mapping. And what this transformation does, and we're going to denote it with a capital T like this, is it takes a vector from one set to another set using a rule. It's going to sound a little complicated, I think, but think about what you know about functions and then put that with this idea and you'll be perfectly fine. You've been working with functions for a really long time, and when you plug in some value into your function, you get an output. And so the transformation is like that function, what it does to the input to give you the output. Okay, so for us, T goes from Rn to Rm, and it's a rule that assigns to each vector x in Rn a vector T of x in Rm. So again, going back to functions, think of this like you plug in x and you get out f of x. So the set Rn is called the domain of your mapping or transformation T. And then Rm is called the codomain of T. Now our notation is given like this. Okay, so this is math notation, and it just lets us know that the function or transformation T maps our vectors from Rn. They start in Rn and they transform to a vector in Rm. And so for x in Rm, the vector T of x in Rm is called the image of x under the action of T. Okay, so these are just names and definitions for you. X is in the domain. When you plug it into your transformation, when you transform it, we're just saying that that result that you get from transforming it, we call that result the image of x. Okay, so you did something to x, and that's called the image of x. The set of all T of x's is called the range of T. Okay, and we'll look at a picture for this in just a second. So I just want to mention the difference between codomain and range. The range is a little bit more specific than the codomain. The codomain is the set Rm that we map to, that our outputs belong to, that set. But the range is very specific. It's all of the outputs. So it's all of the T of x's that come out when you of your mapping or transformation when you plug in x. All right, so here's an image of what we were just talking about. So we have our x in our domain, which is represented by this plane here, just visual for you, which is Rn. And so we apply our transformation to x, and it transforms x to T of x. And then all of the T of x's, remember all those images make up the range. But then the range is part of a larger set, Rm. Okay, so that's just a visual for you. Hopefully that helps a little bit. And so what we're going to do now is relate what we're learning about transformations to what's called a matrix transformation. All right, so for each x in Rn, T of x is actually going to be computed by saying that this matrix A times x. So A is some matrix. We're going to say it's size m by n. And so for simplicity, the way that we denote the transformation is x maps to its result, or its image, by multiplying it by A. So just a quick notation note for you. When your arrow has this little bar on it, it's letting us know that we're looking at the individual elements and how to transform them. So over here, without the bar on the arrow, it's saying we're going from set Rn to set Rm. And then over here, it's saying specifically, you take x and you multiply it by A to get that result. And then if you know the size of the matrix that you're multiplying by, then you can tell which set you're going from and the set you're mapping to. And so if A is size m by n, then your domain is in Rn and your codomain is Rm. So let's put some numbers on there. Let's say the matrix was a 2 by 3. Okay, so 2 rows, 3 columns. Then your domain is R3, or 3-dimensional space, or vectors with 3 entries. And then your codomain is Rm, which would be R2, or 2-dimensional space, or 2 entries. All right, then the range of T is a set of all linear combinations of your columns of A. And that's just because the image from x, so when you say x is transformed by multiplying it by A, is of the form A times X. Okay, so let's take a look at this example and put this all together. So here's our matrix A. Notice the size, row times column, so it is a 3 by 2, 3 rows, 2 columns. We have some other vectors given to us. U is a vector with entries 2, -1. B is a vector, notice, with 3 entries. C is another vector with 3 entries. And we're going to define a transformation, T, from Rn to Rm as just A times X. So this is our rule. Our rule is to go from X to T of X, or Rn to Rm, we're just multiplying by A. So that's the rule. And so here's the rule written out with what we have specifically. We have T of X equals our matrix A times our vector X. And then this would be the result when you multiply. Remember how the multiplication works real quick? It's row 1 from here times column 1 from here. And that's your new row 1. Same thing, row 2 from here times column 1 from here. And that's your new row 2, and so on. All right, so we're going to do a few things. We're going to find T of U, so that vector we were given U, which is the image of U under the transformation T. So this statement here, this is just the definition of image. Then we're also going to find an X in R2 whose image under this transformation is B. So remember, we were given B, and this question here is saying, well, what's X? What's X if we multiply it by A, which is from our transformation, and the answer is this vector B. Okay, and then part C, question, is there more than one X whose image under T will give us B? So these two go together. And then letter D, determine if the vector C is in the range of the transformation of T. So let's go through all of these. So first one, A, we're just asked to compute, find the image of U under the transformation T. So that just means compute T of U. And for us, that just means A times U. So here's A, we were given that. Here's U, we were given that. And we just multiply. And so remember how this goes, and I'll write it out on the side. Okay, so here is how you would get the 5. It's just row 1 from A times column 1 from U. And it's just 1 times 2 plus -3 times -1. That's where 5 came from. You would get this 1 right here from saying 3 times 2 plus 5 times -1. And then the last one, the -9, would be -1 times 2 plus 7 times -1. Okay, just reminding you how that multiplication works. So I want to show you something real quick for how you know what size vector you're going to get as a result from this multiplication. So our matrix A is a 3 by 2 matrix, 3 rows, 2 columns. Then our vector U is a 2 by 1 matrix. And so when we multiply them, let me first remind you of how to make sure you're even able to do this multiplication. Recall that the columns of your first matrix have to match the same amount of rows of your second matrix or vector. And so first we're able to do this multiplication because these match. The columns of A match the rows of B, or U in this case. So then the resulting vector is actually this size here. So if you put these two together, look at your result. It is a 3 by 1. So this is kind of a quick way to just check that you're doing everything correct and that you have the right size result when you do your multiplication. So that's it for part A. Part B, we were asked, is there an X such that when you transform it, you get B? Another way to say that is B the image of some X under the transformation T? And so since our transformation is just A times X, we're just solving this matrix equation, AX equals B. So here's A, times it by X, and does it actually equal B? So the question really is, can we solve for X1 and X2 for this particular question? All right, so then here we go with our row reduction. Notice all this is right here in step 1 is our augmented matrix. The first 2 columns are from A, and then the last column is the answers, which came from B. And then you can do your row operations, which we've done quite a few times, but remember what you can do, and I'll just kind of remind you of how to get a couple of these steps. But you're trying to get your pivot positions in each column. So here's a pivot here, get the zeros below it. Here's a pivot here, get the zeros below it, and then eventually above it, and so on. Okay, so let's see if you know how we get these first two zeros. Okay, so here's how you would get the first 0 in row 2. You would just say -3 times row 1, add that to row 2, and that would be your new row 2. And then for the 0 in row 3, that one's pretty straightforward. You just add rows 1 and 3, and that will be your new row 3. So just reminding you a little bit about your elementary row operations, and then your goal is to get your reduced row echelon form, which is what we have over here. We have 1s in our pivots, and then 0s above and below. And then notice our third row is just all 0s. All right, now think about why this makes sense that we have 0s in the bottom row, because we only had two variables, x1 and x2. And so this is good news, because if we had something else in the bottom row, it would affect what we're actually looking for as far as just a vector with two entries. And so this says 1x1 equals 1.5, and then 1x2 equals -0.5. And so x does exist, and it's the vector with those entries. So if we times a by this vector x, we get the result b. And so yes, the image of this x under our transformation t gives us b. All right, now let's try letter C. Any x whose image under t is b must satisfy our equation that we came up with just a little bit ago. It was this equation here. Okay, and so from our result, when we did our row reduction, we have that there's only a unique solution. Okay, so we got one specific x1, one specific x2, and that's the only solution. And that was from doing our augmented matrix and then reducing it. So there's only one x whose image is b under our transformation t. All right, so the last part, part D, remember the question was, is C, the given vector, in the range of t? So the vector C is in the range of t if C is the image of some x in R2. And so another way to say that is that C equals t of x for some x. Okay, because remember what the range is. It's just the set of images. When we take x, we plug it into our transformation, the result. Okay, so this is another way of asking if the system is consistent. Just ax equals c. So really similar to what we did in part B. We're just using vector c this time. All right, so we have, notice the first two columns of our matrix are from A, and then the third column is the vector c. So you just row reduce this augmented matrix. And then take a look at your result down here. You have this row where we have 0 and then 0 and -35. And so the third equation is making this whole system inconsistent, because this says 1x1, if we reduce it, it would equal some number over here. 1x2 equals 2. And then this says 0 equals -35. It doesn't make sense. And so it's inconsistent. There's no solution. Therefore, because we couldn't get a solution, C is not in the range of t. All right, let's take a look at this one. And now we're talking about what's called a shear transformation. So an example here for this shear transformation idea, let A be this square matrix with these entries. Then the transformation t from R2 to R2 is defined by t of x, which is just going to be A times our vector x, and it's called a shear transformation. And so a shear transformation maps one set to itself. So it could be R3 to R3, R5 to R5, and so on. And so it maps with what we call parallel shifts. Okay, so we'll see an image of this on the next slide. So if t acts on a square 2 by 2 image that we're going to see next, then the result, the transformation, is what we're going to call this parallelogram. Okay, so this is an example visually of our shear transformation. So we have this square that's size 2 by 2. We transform it, but it's still being mapped to the same space, in our case R2. And so it's just like this parallelogram, or think of it sort of like a stretched out square. So if this was an image itself, like a picture, and use like maybe a picture of a face, somebody's face, it would be their face like stretched out and skewed over to the right like this. So the key idea is to show that T maps line segments onto line segments, and then to check that the corners of the square map onto the vertices of the parallelogram. Okay, so for instance, the image of the point U equals 0, 2. So notice this is the vector, we're calling it U, and it's the vector 0 for x1 and 2 for x2, which is this point right here. Okay, or you can even think of it like from the origin with the arrow to 2. But this is what U represents right here. And so what we want to see is that with this transformation, are we going to get this point right here? So let me just label those. Okay, so U is here. We transform it, and we should get T of U, which is right here. And let's see if mathematically we can compute that. And so notice what you get, and it does visually line up. So here was A from our transformation. And if we multiply, look what we're going to get, 6, 2. So 1 times 0 plus 3 times 2 is 6. 0 times 0 plus 1 times 2 is 2. And then look at where you're at here. This is labeled as 2. This is labeled as 8. So this looks like it would be right about 6 for x1. And then it's still at a height of 2 for x2. So that's the computation for T of U with the shear transformation. And then this is a visual representation of it. Okay, and then here's just another corner. The image of 2, 2, if you multiply it by A, you're going to get 8, 2, which if you go back to the visual, that lines up. So T deforms the square as if the top of the square were pushed to the right while the base of the square was held fixed in location. All right, so now what we're going to be talking about for the rest of this section is linear transformations. And so for a transformation to be called linear, both of these two things have to be true. Okay, so we've talked a lot about transformations. You now know what that is. But now we're saying a transformation is classified as linear if, when you transform U plus V, you get the same result as if you did the transformation of U and the transformation of V, and then you added those results. Okay, and then fact 2, if you have C times U, and then you transform that, it's the same result as if you transformed U and then multiplied by C. So if both of these facts are true, your transformation is by definition called linear. And so linear transformations preserve the operations of vector addition and scalar multiplication. Okay, so this here is just what I was mentioning for property 1. It's saying that you can add U and V first in Rn and then transform them by applying T, or you can transform U and V individually and then add the result. And so these two properties lead to the following useful facts. So if fact number 1, if T is a linear transformation, so you know it's a transformation and it satisfied equations 1 and 2, or properties 1 and 2, then also what's true is that T of 0 equals 0. The 0 vector transforms to be itself. So this is always true for any transformation that's considered linear. And then what's also true is that if you have C times U and you add D times V and then you transform that, it's the same as transforming the vectors first, timesing them by the scalars C and D, and then adding them. Okay, and then this is true for all vectors U and V in the domain of T and all scalars C and D. Okay, so if you know your transformation is linear, then you can use this equation here. And so our property 3 follows from the condition of property 2, that T of 0 ends up being 0. And here's just a brief explanation why. And then property 4 is true if you use both properties 1 and 2 to rearrange your equation. And so if a transformation satisfies equation 4 up here, property 4, it must be linear. Why mention this sentence is basically if you have that this is true, so a lot of times what we do is we can check property 4, and if we can conclude that the left side of the equal sign equals the right side of the equal sign, then we can use that to say that our transformation was in fact linear. And so a repeated application of 4 produces this useful generalization. So this is our generalization. And then this is actually called the superposition principle. And so one way you can think about this is think of the vectors v1, v2, and so on as signals that go into some system. And then when you apply t, your transformation, to those vectors, that's going to be the responses of the system to those input signals. And so a system satisfies the superposition principle if the following is true. Whenever your input is expressed as a linear combination, and this could be of the signals, then the response is the same linear combination of the responses to the individual signals. So that's exactly what our equation was saying right back here. So we have a linear combination of our signals, we transform them, and it equals the same linear combination of the responses. All right, and then the last thing to mention is two other linear transformations, two specific ones. So if we have this transformation from R2 to R2, and it's just going to be represented by multiplying R times X, then if your R value here that you're multiplying by is between 0 and 1, then we call that a contraction. And if R is any number greater than 1, we call that transformation a dilation. Okay, so that's it for our introduction to linear transformations.